All right, so next thing we got to talk about is the reaction quotient. And what this does is it allows us to predict the direction that the reaction is heading in at any given moment. So up to now, we've been trying to figure out equilibrium concentrations or the ratio of products to reactants at equilibrium. Now what we want to do is say, okay, we got a reaction going. If we stopped it right here, which direction is it going? Is it going forward or is it going backwards? So to do that, we use something called the reaction quotient. And the reaction quotient has a symbol of a capital Q, and it's the same thing as K, except it is not at equilibrium. So to find Q, you do the concentrations of the products raised to their coefficients over the concentrations of the reactants raised to their coefficients, just like you would with K, except that when you do it with Q, you're at a different point. You're not at equilibrium. Well, necessarily. You could be at equilibrium, but if you're solving for Q and you're at equilibrium, then it turns out that Q is K. So, all right. So here is what happens. Oh, I don't even know what's going on here. All right, there we go. If Q is less than K, Q is less than K. So remember, we have, I keep accidentally hitting it. So we got our products over reactants here. Okay. So what this means is if Q is less than K, that means we have less products, we have a smaller number up top and a larger number at the bottom than we would at equilibrium. All right? So that means it is going further toward the products to get to equilibrium. So that means it's heading in the forward direction. If Q is greater than K, that means we would have more products than reactants at equilibrium. Okay, so the ratio at equilibrium is a certain thing. If Q is greater than that, that means we have too many products and not enough reactants. So the reaction will actually go backwards. And then if Q and K are the same thing, that means we are at equilibrium when we're looking at it. Hopefully that makes sense. So let's try a problem here. We have Kp, so this is the ratio at equilibrium, and then it gives us the partial pressures at a certain point in time. It wants to know, are we at equilibrium, and if not, which direction are we going to go? So let's set this up. The product is the ICL, so we got 0.355 squared over, and remember this is in atmospheres, but that doesn't matter. We're going to do it the same way as we would with concentration. We have a I2 concentration of 0.114 and no coefficient. Then we have a Cl2 concentration of 0.102, no coefficient. So let me type this into my handy dandy calculator here. I got an answer of 10.8. 10.8. So that means that this is Q, and Q is less than K. Q is less than K. That means that we have less product at this point in time than we do when we finally reach equilibrium. Okay? Because at equilibrium, this number is bigger, which means this ratio is bigger. You're going to have a higher amount of product. So if Q is not as big as K, that means we are actually still heading in this direction. We are not at equilibrium, and we're still heading in this direction. On this one, we have concentration. So we're calculating Q and doing the exact same thing all over again. So NO2 is the product, and there is a coefficient of 2, so I'm going to put 0.0255 squared on top. Then on the bottom, I have 0.0331, no coefficient. So 0.0255 squared divided by 0.0331 gives me 1.96 times 10 to the negative second. So this number is larger, than this number. This number has a smaller exponent there. So if that means in this case, that means we have more product than we do at equilibrium. If we have more product than we do at equilibrium, the reaction is going to go this direction until it gets to equilibrium. So not at equilibrium, and it's going to the left toward the reactants. All right, good deal.